Welcome everybody. This is a joint LIDS and TOC seminar. I think we're running a bit late, so I'll make my introduction super short. We're super happy to have Ankur here. I think you all know Ankur, so I don't need to say a lot other than I think we're in for a treat.
Thanks, Pablo. All right, it's nice to be giving a talk at MIT. Actually, it's been a couple of years for me, so thanks for coming. I'll be talking about learning from dynamics, and this is based on joint work with some amazing collaborators, Ainesh Bakshi, Alan Liu, and Morris Yao. So in this talk, I'll be interested in the problem of learning the parameters of a linear dynamical system from its trajectories. This is a very basic and fundamental problem in control theory. It's been studied for over 60 years, and nevertheless, there are very wide gaps in our understanding. So my goal in this talk is to fill in those gaps. So let me tell you about what a linear dynamical system is and why they're so important. So these are the two defining equations for a linear dynamical system. Now there are quite a few moving parts, but let me go through them slowly. The important thing is that there's a hidden state, xt, that's an n-dimensional vector that evolves over time. Now the catch is that we don't directly observe the hidden state. Instead, all we see are the input-output behaviors of the system. So at each time step, we see the input, which is some vector ut that's applied as a control to the system. And we see some output yt that's another vector. Now each of the matrices that show up in these defining equations, they have a special role and special names. The most important of which is the transition matrix A. That's a thing that governs how the system would evolve on its own in the absence of control. And a lot of its spectral properties control things like what the system would look like in steady state. So we also have the control matrix B that describes the relationship between the controls that are applied and how they affect the hidden state. And last but not least, we have the sensing matrix and the feed-through matrices that just describe the linear relationships between our observations, the yt's, and what's going on under the hood in the system, namely how they depend on the underlying system state and control. So the last point I want to make is that usually in LDSs, you think about the system as being stochastic, so it's not a deterministic process. And there's some amount of jitter, so there's some sort of process noise that affects our hidden state, and there's some observation noise that affects our observations. For the purposes of this talk, you can think about these as Gaussian random vectors, although the algorithms I'm going to give you are going to work in much more generality than that. So this is the model we're going to care about, and let me tell you something about why it's so widely studied and widely used. Some of the most famous applications of linear dynamical systems comes from robotics, navigation, and tracking. In fact, there's a very famous example. It was used in the literal moon landing. So here the idea, this is a sort of prototypical application. You have some object that's moving. In this case, it's the space shuttle on its trajectory from the Earth to the moon. And at each time step, you get very noisy measurements of where it is. Now, what you'd like to do is you'd like to use your knowledge of physics to find a much better estimate for the underlying trajectory that's hopefully much closer to the ground truth. It turns out that if you model this system as a linear dynamical system, there are very effective methods for estimating the underlying trajectory. Those are called Kalman filtering. In fact, they won the 2008 Medal of Science exactly for their role in the moon landing. But at the end of the day, what you have is a very simple instance of this abstraction. It's a linear dynamical system in which the state of the object you're tracking is just defined by its position, its velocity, and its acceleration. And then your transition matrix describes how these quantities change. Namely, this transition matrix describes the laws of motion because it describes the way that the velocity affects the position. It describes the way that acceleration affects the velocity. But at the end of the day, what you have is a linear dynamical system. So there are tons of applications in radar science and robotics exactly along those lines. There are other applications in natural sciences where sometimes what happens is you have some natural process that's evolving over time. And one of the most powerful ways of modeling that system is as a linear dynamical system. So this arises, for example, in biology and epidemiology. In fact, there's one particular epidemiological problem that's been on all of our minds for the last couple of years, which is namely how COVID spreads. And it turns out that the simplest model for how a disease spreads, you can think about as a very simple linear dynamical system, because one of the simplest models is what's called the SEIR model. You divide your population into 4 categories, depending on whether they're susceptible, they've already been exposed, they're currently infected, or they've been recovered. And your state vector just describes how many people are in each of these different categories. And in this case, your transition matrix A are just the transition rules in some state machine that describes with what probability you transition between the different states. If I'm exposed, what's the probability that I then become infected, and so on. In fact, the data that I'm plotting right here is from a very recent study in which they do a fancier version of this, where it's an age-stratified SEIR model, where you fit the parameters of this model differently depending on which age group you fall into, and they find very good results for tracking real epidemiological spreads. There's one more application which I'll go through, which is a neat one that I learned about recently, which comes about through medicine. So in a lot of medical applications, you want to understand the efficacy of some drug. And the gold standard for how exactly you can figure out its effectiveness is by doing what's called a randomized control trial. So here you take a very large cohort of patients, and then you randomly divide them into 2 groups. One of the groups you give the drug to, and the other group you give a placebo to. And you measure the effect of these interventions on the 2 populations. And then that gives you a way to figure out how effective the drug is. But it turns out that there are a bunch of medical applications where it's really not feasible to create a very large cohort of patients. In some cases, it's just not possible, or in other cases, you want to understand the effects of a drug on a person-to-person basis. So that might sound like a hopeless task, but it turns out that there's a very productive way to think about this through the lens of linear dynamical systems, because you can do experimentation on just one person, where you randomize week to week whether you give them one drug or another drug, and you measure the time response that you get, and you try and learn properties of the underlying linear dynamical system as a way to try and measure the efficacy of the drug. So this is by no means a set of exhaustive applications. There are a lot more that come from speech processing, econometrics, finance, and so on. But this should hopefully give you a flavor for why linear dynamical systems are so beloved and widely studied. And taking a step back, if we think about these 2 defining equations and the abstract model we have for a linear dynamical system, we can think about what makes them powerful. And it really comes from the fact that when you have a linear dynamical system, there's a lot that you can do with it. So in fact, the part that I already discussed that has to do with Kalman filtering is really about the inference problem, which is if I gave you the parameters of the linear dynamical system, namely I told you the matrices A, B, C, and D, then you could ask to try and estimate the underlying hidden state. So that's an inference problem, and it's an inference problem for which there are very good solutions. It turns out that things like Kalman filtering do remarkably well. So once you have the parameters of an LDS, there's a lot you can do with it. In this talk, what I'll be interested in is really the question that comes before that, which is, what if you don't actually know the parameters of your LDS? How can you try and fit them to data? There are some applications, like in the space shuttle example, where they come from prior knowledge about physics. And yet there are other applications in areas like biology where they're really natural processes that we want to understand better, and we'd like to reverse engineer what are the governing dynamics based on observing the process. So what I'm going to do in the next part of the talk is I'm going to work towards formally stating what the problem is. First, I'll do it a bit informally, and then we'll work towards the more formal description of it. So put simply, I want to learn the parameters of an LDS. But in fact, I'm going to make my life as difficult as possible, because I'm going to try and learn it from just one single long trajectory. And keep in mind, what I'm observing this trajectory is I see the input-output behavior. I see the sequence of inputs, the U1 through UTs. I see the sequence of outputs, Y1 through YTs. And then I want to try and use those samples to try and estimate in some meaningful sense these matrices A, B, C, and D. Now actually, in the standard nomenclature of control theory, I find the nomenclature of inputs and control to be a bit of a misnomer. I'm actually not going to assume that I can control these things. I'm just going to assume that they're random. So you should really think about them as a disturbance. So if I disturb the system randomly, but I see how I'm disturbing it, then based on the output that I get, can I learn what are the governing properties of how the system works? Now, even here, this is a bit of an informal statement because it's not so obvious how to define what I mean by estimating the parameters A, B, C, and D, because it turns out that there are some types of transformations that leave the linear dynamical system invariant. So it's not just possible to learn the underlying matrix in Frobenius norm, but I really have to define the right parameter distance to make this problem make sense. So let me tell you about a very strong goal, which is I'll say that two linear dynamical systems are equivalent if there's no adaptive strategy that distinguishes them. So what I mean by that is you choose some adaptive strategy for how you're going to set the next input, ut plus 1, and that could depend arbitrarily on the sequence of previous inputs and outputs. But I want the property that these two LDSs, that one of which I'm getting samples from and the other one I've learned, I want the property that even for adaptively chosen sequence of inputs, they still generate the same output distribution. So this is a very strong notion of what it means to learn an LDS. It means that I've learned all of its possible input-output functionality. But for our purposes, it translates into something very simple and elegant, which is that in the case where you have Gaussian noise, it turns out that two linear dynamical systems, one defined by A, B, C, and D, and the other defined by A hat, B hat, C hat, and D hat, are equivalent if and only if there's a way to transform parameters from one into the other. Yeah?
By the small gain theorem, is it also equivalent to say that this is just H infinity recovery of the system?
I think that's a little bit subtle. Let me answer that a little bit later, because I think it has to do with some resolvent properties, but very good question. All right, so here what I'm asserting is that these two linear dynamical systems are equivalent if there's some sort of invertible transformation U, so that, for example, their transition matrices are equivalent up to conjugation. So the way to think about this is that I never directly see the hidden state. So I can always apply some reparameterization of the hidden state in such a way that I don't actually change the input-output behavior. That's exactly what this proposition is capturing. But for our purposes, what this really means is it defines a very natural notion of parameter distance. So now I can make my problem precise, which is given one long trajectory, I'd like to learn good estimates that are close in that metric that I just implicitly defined on the previous slide. I want that after some unknown transformation U, because it's not possible to perfectly learn A, but after that transformation U, I'm epsilon close in Frobenius norm. So this is the main goal for the talk. And what I'll be interested in is there a polynomial time and sample complexity algorithm for learning? In fact, it turns out that even the sample complexity is not so obvious. So it's no exaggeration to say that there have been thousands of papers on learning linear dynamical systems. There's quite a wide range of assumptions that are used in there. But oftentimes, what you don't get a good sense for is whether the assumptions are actually necessary or not. Let me tell you one particular assumption that's very common and very popular, but I'm going to argue that it's actually quite unreasonable. So this is an assumption which is called strict stability. So here what I can do is I can talk about the spectral radius of a matrix, which is the largest absolute value of any of its eigenvalues. And what I'll be interested in is the spectral radius of my transition matrix A. Remember what I told you, that the spectrum of the adjacency matrix tells you a lot of important information about the long-term behavior of your system. Now, if you assume that the spectral radius is strictly less than 1, that's called strict stability. And if in contrast you assume that the spectral radius is less than or equal to 1, that's called marginal stability. Now, these two things might sound like they're very similar to each other. They just differ in whether an inequality is strict or not. What I claim is that they actually make a world of difference, and I'll give you a bit of a hint of this on this slide, but we'll see it more later when we get into the technical parts. So first, what I claim is that strict stability, it fails even in very simple cases. In fact, in cases we've already seen. So if you think back to that space shuttle example where the transition matrix describes how the velocity changes the position and how the acceleration changes the velocity, what you end up with is you end up with an upper triangular matrix with ones along the diagonal. So you definitely are not strictly stable. And this is usually what happens when you discretize an ODE. You get something with ones along the diagonal, and you just don't have strict stability. Maybe more importantly, the thing which really goes out the window is that strict stability is in effect a restriction that your LDS does not have long-range correlations. So the way to think about it is that if I told you the hidden state at some time step t, and I asked you what effect that knowledge had on what the system looks like at some much later time, when you have strict stability, it would have exponentially little effect. And that's because when I take higher powers of my adjacency matrix, everything is decaying to 0. And maybe another way to think about the weakness of strict stability is that I set my goal as trying to learn an LDS from one long trajectory. But in effect, because you have no long-range correlations, it means you can actually get as many samples as you want, because you just wait a long enough time and then everything that happens later will be independent of whatever happened before. Now, in contrast, marginal stability is a much more tame assumption. It's really there so that the system doesn't explode. It turns out that even when the system does explode, you can still hope for learning guarantees. It's just that assuming that the additive noise is some small fixed amount doesn't really make sense. So for the purpose of this talk, I'll just take marginal stability for granted. And the way to think about it is that works that assume strict stability, they usually have this type of dependence sitting in the theorem someplace. So they have some dependence both in the running time and sample complexity that looks like 1 over 1 minus rho of A. So it's something that degrades very badly as you approach 1. And that's really from the effect that you just wait this many steps and things become independent. It's the same property at play. So what I'm interested in is really a qualitative question, which is when we have learning in LDSs and they do have long-range correlations, do long-range correlations fundamentally obstruct learning? It'll turn out that the answer is no, and that there's some pretty cool mathematics that goes into solving this problem. So I just told you which assumptions I don't like. Let me tell you which assumptions I think are much more reasonable, because these, as we'll see, are much closer to information theoretically minimal assumptions. These are old assumptions that go back to the roots of control theory. And these are matrices that are going to show up a bunch in the analysis, so I'll spend some time to make sure that we understand them. What I can do is I can define the observability matrix, which is a block matrix. The first entry in the block matrix is C, which, remember, is the matrix that describes how our observations depend on the hidden state. The next entry in this block matrix is C times A, and after that it's C times A squared, and so on. And what I claim, this is a very simple claim, but it's powerful, is that if this matrix doesn't have full column rank, you're in trouble. In particular, there's some portion of the state space that you just don't get to see, even if you aggregate observations over S consecutive time steps. So the proof for this is very simple. I'll just give a sketch of it. The way that this works is, imagine that my state is at xt, but I hypothetically imagine perturbing my state in some direction z that's in the null space of this matrix. Then we can think about what it means to perturb the state in that direction z and how it changes our observations. We can think about, our first observations really depend on c times xt, but because z is in the null space, it doesn't change anything. And that means that it has no effect on our observation yt. And then if you think about what the next entry in this block matrix is, it's not c, it's c times a. This means that if I perturb my state, then it'll have no effect on the next observation, yt plus 1, and so on. So that's the basic idea, is that if you don't have observability, there's some part of the state space that you're just blind to. It turns out that there's a dual assumption, which is the other piece of the picture, which is called controllability. So remember that the B matrix describes the relationship between your inputs and how they affect the hidden state. So I can form this block matrix, which is B, AB, A squared B, and so on. And now what I claim is that if this matrix doesn't have full row rank, you're in trouble. And that's because there's some direction in the state space which your input can never push you in. And so the necessity of these assumptions actually goes back to Kalman in the 1960s, where he showed that if the observability and controllability don't have full column and row rank respectively for all orders S, then the problem is fundamentally impossible. So the thing which we show is that it turns out when you quantify these assumptions, you can actually get a fully polytime algorithm. So as long as I assume that the observability and controllability matrices are well conditioned, I can get polynomial guarantees for my running time and sample complexity, learning from just one single trajectory, even under this weak notion of marginal stability. And in fact, the running time and sample complexity depend polynomially on those condition numbers. So this is, in a sense, the right way to quantify these assumptions that go back to Kalman. And you can prove an almost converse to the statement that if these things aren't true, then the problem is really information theoretically impossible, with just the difference that I'm going to say that imagine observability and controllability are ill-conditioned for all orders S, then you can show that that instance is information theoretically impossible to solve with polynomial sample complexity. Yeah?
It seems like from your argument you could get some of the parameters.
You could get some of the parameters, that's right.
And so there's like a well-posed, a goal you could state reasonably.
That's right. So I'll talk more about this later, but let me give you a short answer to this, which is my real goal in this talk is to try and build a bridge between learning theory, a lot of standard tools in theoretical machine learning, and linear dynamical systems. And usually in learning theory, we have a hierarchy of different goals, like parameter learning, where I want to learn all the parameters, proper density estimation, where I merely want to find something from the class that agrees, and improper density estimation. Usually parameter learning is the easiest one to think about necessary and sufficient conditions. This is really step one. And that's a very good question about what happens for step two.
I guess more generally, is there anything which is, so you're saying there's some things you can learn in polynomial time and some things you can learn never?
Yeah.
So is there any part of the regime that's exponential time?
Well, so the point is that what these show is that if you can create instances which are exponentially ill-conditioned, or that exponential depends on the dimension of your system, then the condition number really is an obstruction to solving the learning problem. But there are more subtle things which are that, what if it's ill-conditioned because there's a single bad singular vector? Then there are still parts of your system you could hope to learn, but that's a much more nuanced treatment, which I don't know yet. All right, any other questions? All right. Okay, so in fact, there is one really cool paper that does solve learning under marginal stability, but with a caveat. This is a work of Simchowitz, Bokar, and Recht, where they give an algorithm that works under marginal stability, but it has a catch that it has an unspecified dependence on the system parameters. So in fact, it can be exponential even in cases where we can get polynomial time guarantees. Yeah.
Were you guys able to show that that thing that we get actually is exponential?
Yeah.
Oh, really?
Yeah, that's right.
Basically, okay.
Yeah. We can talk about that offline, but yes. Okay. All right. So I want to give one more piece of motivation, which is that, these things have been studied in control theory since the 60s. Most of the work back then was really on ineffective bounds. There were asymptotic guarantees that you could learn something in the limit. Now these days, in the last 10, 15 years, people have been focusing a lot on getting effective bounds. And one of the reasons there's been renewed interest in control theory actually comes from applications in deep learning. So there are these things called recurrent neural networks that are basically, a non-linear version of what I'm telling you about. And people wanted to understand how gradient descent works at fitting the parameters of an RNN. And the trouble is that fitting the parameters of an RNN is very difficult to prove theorems about. So a lot of work study LDSs instead as a metaphor for trying to understand what is happening in the nonlinear case. But there's this funny quirk that, if you're studying it because you care about SGD, sometimes you miss what are the fundamental algorithmic limits. So that's one of the main things I'm preaching, is that by studying the problem purely algorithmically, we'll get a much better handle on when the problem is or is not tractable. All right, so that was enough pontificating. I think I should roll up my sleeves and tell you some cool techniques. The fun thing is I can give you many of the most important proofs just in the next 25 minutes. So let's do that. And in fact, we're going to follow a blueprint, which, if you're in theoretical machine learning, and if you're not, I want to tell you about it. See, over the past 10, 15 years, there's been a lot of progress on provable algorithms for learning all kinds of models. like hidden Markov models, mixtures of Gaussians, topic models, and so on. And it all follows this old and ancient blueprint that goes back to Karl Pearson back in 1894, where the idea is that you have some parametric system you want to estimate the parameters of. And what you do is you take your data and you use it to estimate the moments of your unknown distribution. You use those empirical moments to set up a system of equations. Usually it's a system of polynomial equations. And then you solve the polynomial equations some way, somehow. And hopefully you show that the solutions to your system really are provably good estimates for the parameters you wanted to learn. Now this approach goes back to 1894, but it was mostly a heuristic. But in the last decade or so, there's been a lot of work in giving actual rigorous guarantees that follow this blueprint for all kinds of different models. But I want to emphasize that this is really in a restricted setting because it's in a stationary setting. There's one fixed distribution and you get as many samples from it as you want. What makes LDSs much more challenging is that they're non-stationary. I have one long trajectory and that the distribution of that trajectory is changing over time as I evolve the system. So what I want to know is whether there's a way to set up this blueprint to work outside of the usual applications, maybe for non-stationary settings. So we're going to do the easiest possible thing is we're going to use the method of moments. So there's something very important, which I'll explain more about later, which are called the Markov parameters. It's just given by this definition. It's another block matrix. It's given by D, CB, CAB, and so on. And I'll give you more intuition later, but the way to think about it is that it represents the input-output behavior of your system. So we're going to follow a very simple two-step procedure. We're going to estimate the Markov parameters, and then we're going to use the Markov parameters to estimate A hat, B hat, C hat, and D hat. So that's our blueprint. And in fact, even better, step 2 has already been done for us. It was done in the 60s. So let me tell you about this very famous algorithm, which is called the Ho-Kalman algorithm. I should confess that, when I saw this, I tried to read the original paper and I got confused. So let me give you a slightly different proof that I think is a little bit simpler of the Ho-Kalman algorithm. What you do is imagine someone gave you the Markov parameters of your LDS. What I'm going to do is I'm going to form a block Henkel matrix. You should not see why I'm doing this yet, but hopefully it'll be revealed as I do it. So I'm going to form this block Henkel matrix. You notice that the entry in the top left corner is the second entry in my Markov parameters. Then along the next diagonal, I have the third entry in my Markov parameters, and so on. And the important thing is that if you gave me the Markov parameters, I could write down this block Henkel matrix. And the other important part is that, actually, let me tell you something first, which is one more piece of notation. I'll call the overall Henkel matrix H. And for reasons that should not be clear right now, I'm going to take all but the last block column and call it H1. And all but the first block column and call it H2. So this is just notation. But now we can already see some of the intuition. You remember the observability and controllability matrices that I told you about earlier, right? So the observability matrix was C and CA and CA squared. And the controllability matrix was B and then AB and A squared B. So what I claim is that the Henkel matrix is just the product of the observability and controllability matrices. That just follows definitionally. So that's great because what this means is that we have the left-hand side. Someone gave me the Markov parameters, so I know H. And the right-hand side describes a factorization that I wish I had. If I had it, I would be able to estimate the things I set out to do. So let's think about how we're going to execute the rest of this algorithm. The idea is very simple. We know that the thing we want corresponds to some factorization of H. We're just going to find any other factorization of H and show that it really must be equivalent in the way that we want. So what I can do is I can use my old friend, the SVD. I'll take the H1 matrix instead of H. I can write it as U times sigma times V transpose. That doesn't look like the product of two things, so I'm going to take sigma and split it into two pieces, sigma to the 1/2 and sigma to the 1/2. And very suggestively, I'll call the first part of this factorization O hat, because I hope it's close to O. And I'll call the second part Q hat, because I hope it's close to Q. And remember that the same way that H could be written as sum O times sum Q, the same way H1 is sum O times sum Q. I just change what order I go out to because I lopped off the last column. So now I know that, on the one hand, H1 equals O hat times Q hat, and it also equals O times Q. And now some simple linear algebra is going to get us off to the races, right? Because what I claim is that if the observability and controllability matrices have full column and full row rank respectively, there's no choice, but they have to differ by some invertible linear transformation. Otherwise, they wouldn't have the right column space. So now we're in good shape. This is exactly the notion of equivalence that showed up in the way that we set up our learning problem formally, is this is the underlying transformation that I want to be equivalent up to. So now we're almost done. We're almost home free. The last thing we have to do is we have to estimate this key matrix A. And now I can use H2, which is the other missing piece. Remember, H2 was all but the first block column. So if I remove the first block column, I always have at least one power of sitting in my Hankel matrix. So you can write H2 as O times A times Q. And now we're in good shape because from step 2, we know that there's a relationship between O and O hat that differs by this transformation T. And now what I can do is I can just left multiply by the pseudo inverse of O hat and Q hat, and that's going to give me A hat up to the similarity transform exactly like I promised. So that's the proof. I still don't understand the original proof in the paper. If you do, come talk to me. But this is a sort of more modern proof that is related to tensor decompositions, and I'll say more about that later, but I think this might be a better way to think about it. All right, so in principle, what I proved for you is the second part. Actually, I proved a weaker version than what I really need, because I showed you that if someone gave me the exact Markov parameters, I would be done. The trouble is no one's going to give me the exact Markov parameters. At best, I can get some additive estimates to them, because the first step, I'm using actual data. So the thing you would really care about is whether there's a stability analysis of the Ho-Kalman algorithm that shows that even in the presence of sampling noise, you still get provably good estimates of the underlying parameters. And that was done recently in a paper of Oymak and Oze. It's a very nice paper, but personally, I think you should think of this as fairly intuitive because it follows from the stability analysis of the SVD. It turns out the SVD is stable exactly when those things that diagonalize the matrix are well conditioned, which again has to do with the condition number of observability and controllability. So the same property that we cared about. So let me tell you about the main challenge. See, nothing was really new here, but now I get to tell you in the last few minutes about some exciting new techniques. See, the first step we have to solve is how exactly we get these Markov parameters. And now we're going to see a lot of cool things come into play again, like why the problem is actually fairly trivial when you have strict stability, and what you can do in the face of long-range correlations. So the first thing I'm going to do is I'm going to convince you that the problem is dead trivial to try and estimate the Markov parameters. But then there'll be a catch. It won't be quite so trivial. There'll be a very important catch. So first, it turns out that there's a very simple way to create an unbiased estimator of the Markov parameters. I told you the way to think about them intuitively as is the input-output behavior of your system. So let's do exactly that. Let's measure the correlation between the input and the time-lagged output. Let me look at the expectation of yt plus j against ut transpose. And what I claim is as I change j, which is the lag between my input and output, I'm going to get all of the Markov parameters as I sweep out. That's the key point. So, once I make this claim, there can only be one proof of this fact, right? Which is you just unravel the recurrence and check it. So let's do it for j equals 1, because I'm lazy. So yt plus 1 is equal to this equation right here. That was the first defining equation from the second slide. I don't see any UTs in there, so let me unravel the recurrence some more. And now I have some UTs showing up. UT is independent of everything else because I'm going to assume that it has identity covariance and it's independent. And that means that I look at this expectation, the only thing that gets picked up is the second term, the one that has CB, which is exactly what I claimed in this, right? So that's the proof. So now it looks like I'm done because I said, if I have the Markov parameters, Ho-Kalman saves the day. And there's a very simple naive estimator that's an unbiased estimator for the Markov parameters. So I should be done. Let's do this a bit more precisely. So what could I try? I could try averaging these estimates over different time steps. Each one of these in isolation is an unbiased estimator of the Markov parameter I care about, and I average them up over all of my capital T time steps. But I claim there's a big catch here, which is where the action is happening. Anyone want to catch me in a lie? Yeah. Oh yeah, that's the whole problem, right? The noises are dependent. So in fact, this doesn't have unbounded variance. This doesn't have bounded variance, it has unbounded variance. That's exactly right. That's the heart of the problem. See, what I told you earlier was that the problem becomes really trivial when you have strict stability. That's because I can just wait long enough until I get new samples, and then this naive algorithm does work. So this is very funny because people write lots of papers on analyzing SGD because they care about recurrent neural networks, but they do it in cases where the problem is strictly stable. And it turns out that in that case, the problem is actually quite easy because we would be done. But let's work harder. So I claim that there is a way to solve this problem, and this is where the cool math is going to come in. Let's try and engineer a better time series. The whole game here is if I knew the linear dynamical system, which I don't, I could show that there's a way to transform the time series that fixes and stabilizes my estimator. So what I want is I want to create a new time series based on these coefficients Cj, so that these new time series, these y hat t's, have two properties. First of all, I want to maintain the fact that it still gives me an unbiased estimator of the Markov parameters because I want to estimate them. But secondly, I want that it fixes the variance problem. I want that there's some way to choose these CJs so that this new estimator, expectation of y hat t plus j times ut transpose, has variance that's bounded independently of t. And if I can do that, I would be in good shape. So we'll go through a couple attempts to solve this problem. Let's do the first attempt, which is one thing we could do is if I knew the LDS, what I could do is I could look at the characteristic polynomial of the transition matrix. And I could set the CJs based on the coefficients in the characteristic polynomial. So the important thing for us is really just the Cayley-Hamilton theorem, which tells us that every matrix satisfies its characteristic polynomial. Or to put it another way is that I can express a to the n, a is an n by n matrix, as a linear combination of lower order powers of a. And in fact, the coefficients in that expression are the CJs. So that's the Cayley-Hamilton theorem. And what I claim is that if I use these CJs to engineer a new time series, what I'm going to do is I'm going to cancel out everything but some transient terms that are going to be of polynomial variance. So the only way to prove this thing is, you write out a giant equation. I tried that. It didn't fit on the slide. I tried to remove more terms. It still didn't fit on the slide. And really, it's a bit of a shame because there's nothing interesting happening in that equation. So let me give you the spirit of the proof without actually writing out the proof. Let's pretend our LDS were simpler. There's no process noise. There's no observation noise. The D matrix is 0. And let's think about why we create the right cancellation. So I'll write out the y hat t plus 1 in terms of the other y's. That's just the definition of my engineered time series. I can use the expression for how y depends on x. I can organize things based on which u's show up in them, because I'm going to want to try and create cancellation. And then what I can do is I can expand xt plus 1 in terms of ut and xt. And then I can take these two terms and I can expand them in terms of ut minus 1 and xt minus 1. So along each row, I'm collecting together all the different terms of the uts. And I keep doing this, and you start to see the pattern. And the point is, if you look at this last row, what's going on? I have a high power of a, but I'm canceling it with lower order powers of a. And I've chosen these c's exactly according to Cayley-Hamilton so that I create cancellation eventually. You won't get cancellation on the first row because there's only one ut, right? But eventually, as I get enough terms in my contribution, everything will cancel out. So that's the main point. So if you work out the math, even in the simple case, what happens is you get this expression where a bunch of things go away, and you just get this much smaller term right here, that yt has some dependence on the ut's, but they don't go arbitrarily far back. They have polynomial size. And then the important thing is that this term right here has polynomial variance. So now it looks like I'm in good shape, right? Now that solved problem 2 because, through engineering, by choosing these CJs according to the characteristic polynomial, we figured out how to cancel all but the transient terms so that we prevent the variance from compounding over the time series, even when we have marginal stability. There's a different problem, which is I destroyed property 1. So what I care about is keeping this unbiased estimator still having the right expectation. The trouble is if I write out that last equation from my previous slide, and I look at the covariance between y hat t and ut minus I, you can see one of the Markov parameters is sitting right there. That's what I want. But there's a whole bunch of other garbage happening that also affects that coefficient. So here there's a very simple fix, which is instead of looking at y hat t depends on yt and yt minus 1, why not just wait a little bit before you start adding up previous terms? So what if I embed some lag so that I don't even start subtracting terms until r time steps have passed? In this case, the point is that none of these early UTs show up, so in this way I don't actually change the expectation. So now we're in good shape because we can cancel out the long-range dependencies so the variance stays bounded. There's a third problem we have to fix, which sounds kind of strange because there were only 2 properties I cared about, so why do I need a third attempt? That's because I lied. The place where I lied is that who says that the coefficients of the characteristic polynomial can't be exponentially large? In fact, there are a bunch of analyses in this literature where they make exactly these kinds of assumptions, where they have bounds that depend on the L1 norm of the vector of coefficients of the characteristic polynomial. It turns out there's a better thing to do. I'm just going to sketch this. It's that what I really care about is expressing high powers of A in terms of lower order powers. So once I have well-conditionedness of observability and controllability, that actually follows that the coefficients are bounded. So it turns out that if you already knew the observability and controllability matrices, then it would imply the existence of good bounded coefficients that cancel out long-range dependencies that preserve the variance. But at the end of the day, this actually sounds kind of circular because I want to learn what the observability and controllability matrices are, right? So how can I use this style of reasoning? Well, the idea is that I can instead write down a convex program to search for the right estimator, and now I know that that convex program is feasible. I should mention that in the real version, the CJs won't be scalars, they'll be matrices, but let's pretend for now they're scalars. So the idea is I can write down a feasibility problem where I look for bounded coefficients Cj that have the property that for my new engineered time series that they induce, that time series remains bounded. And once I know, all of this arguments that I went through the first, second, and third attempt, that's the part that tells you that this convex program is feasible. The harder part for the analysis is that you then have to show soundness, that any solution to this feasibility problem induces a good estimator. But the way that you do this is very similar to the things that I sketched out. The same way that I looked at the cancellations induced by the choices of C, I can define some potential function that describes how much variance has not been canceled out. And that potential function you can show through anti-concentration that if that potential function is large because you haven't canceled things out well enough, then with high probability, one of these constraints will be violated. So that's ultimately how the proof goes. I can't give you the full proof, but that's roughly the idea. But I want to take a step back in the last couple of minutes and philosophize some more. I've spent a lot of time thinking about theoretical machine learning problems like HMMs and GMMs. And those are what I would call the stationary setting, where there's one fixed distribution and you get many samples from it. Usually, estimating the moments of the distribution is trivial. You just take a bunch of samples and estimate them with the plug-in estimator, that's it. The hard part is usually showing what's called identifiability, that if you have a set of parameters that actually matches the true moments, then it better be the case that the true parameters match your estimates match the true parameters. So that's usually where all the hard work goes in. There's a lot of tools from tensor methods that go into showing that uniqueness. But in the context of LDSs, it's actually completely flipped, right? We wanted to identify the Markov parameters, and we had a very simple, naive estimator that in one line I proved for you actually gets the right expectation. The hard part is on the other side, which is how do you actually estimate the moments of your distribution? And that's where we actually had to turn a lot of control theoretic ideas on their head, because the idea was to use insights from control theory to stabilize the estimator in an analogous way to how you use control theory to stabilize a system. We wanted it to stabilize the behavior of our estimator, and we ultimately did it through convex programming. So I'll very briefly mention that I hope this is just step one in a broader agenda, because there are a lot of ways in which I can see the tools from theoretical machine learning potentially being adapted to a lot of non-traditional settings, non-stationary settings like LDSs, or maybe settings like reinforcement learning. And there are a lot of interesting bridges to build, so let me give you a little bit of a teaser. One of the things that we often study in theoretical machine learning is what happens if your data doesn't look the same, like it's not just one Gaussian, but it's some heterogeneous data that looks like a mixture model. You can ask the same types of things even for LDSs. What happens if I don't get samples from one LDS, but instead every time I get a short trajectory, I roll some die and that determines which of the LDSs I get my trajectory from. There are a lot of applications in areas like biology where these are very natural models to consider. There's a beautiful recent work in ICML due to Chen and Poor, where they gave a clustering-based algorithm for learning mixtures of linear dynamical systems in the fully observed case, where you actually observe the hidden state. And the idea was somehow, through a lot of work, trying to cluster the trajectories into which of the LDSs generated which subset of the trajectories. But it turns out that in a lot of mixture model applications, you can actually solve the learning problem even when it's fundamentally information theoretically impossible to solve clustering, because you can argue instead through the moments and through tensor methods. It turns out that it's pretty simple to get a generalization that works exactly along those lines, because that proof I gave you of Ho-Kalman, it was really based on algorithms in tensor decomposition, something called Jenrick's algorithm. And it turns out that from that vantage point, it's very easy to define tensor spectral generalizations of Ho-Kalman, where instead of doing things like measuring the input-output behavior with a single lag, you look at it across a set of lags, and there you use higher order tensors to try and extract more information. So it turns out that there's a polytime algorithm even for learning mixtures of partially observed LDSs under some very natural joint non-degeneracy assumptions. All right, so that's about all I wanted to say. So hopefully what you got out of the talk was you understand what a linear dynamical system is and why they have so many cool applications. Linear dynamical systems are really interesting in a lot of applications precisely because they have long-range dependencies. But long-range dependencies doesn't obstruct learning. It turns out that there are ways to tame the long-range dependencies by conditioning your estimator and stabilizing it in the right way. And we used convex programming to guide our choice of the right estimator. And what I would love to understand is whether these ideas can be taken much further. Is there some kind of dictionary that maps tools from unsupervised learning to their dynamical counterparts? So if you want to know more about that, come talk to me afterwards. But in my other life, I spend a lot of time talking about RL these days. So I'll stop there and take any questions you guys have. Thanks.